Dsage is basically this package for Sage that lets you do parallel computing relatively easily. And it's really designed for parallel computing where the patterns kind of, you have these very coarse-grained jobs, which means that if you have this task you want to do, you can split it up so that each subtask doesn't have to talk to the other tasks so much. I see some CS folks here, so some of you might have taken the Google course, and they might have talked about MapReduce, and it's kind of like very similar in that sense. So does everyone kind of understand the idea of parallel computing? Cool. All right, so I'm just going to go ahead and just give you a quick demo on how to use it. So let's see. Ooh, where's my mouse? Okay, so from Sage 3.0, which is about to be released soon, you just start Dsage, and then to get a Dsage server and workers and a client up and running, all you do is do d equals dsage.start all. And they'll run a 2 workers by default and the server. And then you can just send the jobs like this. So you can say j equals d, and then you can say 2 plus 2. And they'll create a job, put it on the server, and some workers will go and fetch it and then process it. And if you do j.wait, it'll wait until some worker's done the job, and then you can just get the result, which is 4. And
can you move over a little? Because you're in front of the projector.
Oh, sorry. And since I think Sage 2.11, we've also had a web interface, which doesn't. How do I switch off the inverse?
Just hit Control-Alt, Command-8 yet again to toggle it.
Control,
just
all
the 3 keys to the left of the.
Gotcha. So since a couple of versions of Sage ago, we've also had a web interface, so you can actually monitor your jobs and see exactly what happens when you run a job. So for example, if we submit this job again and switch to the web browser, you can see that we've got a new job, and in a little while it'll switch to processing, and then a little while it should be done, hopefully. There you go, and it's completed. And you can click on it and see some information about the job, like its output and the worker that is done by, et cetera, et cetera. So this is a really quick introduction to Dsage, and the topic today for William's lecture is cryptography, and one of the interesting parts of cryptography, or public key crypto, is the challenge of factoring numbers. And there are actually some really cool methods of factoring numbers that lend themselves to parallelization. So Robert and I wrote this algorithm called distributed factor, which actually uses those algorithms, which are the elliptic curve method and also the quadratic sieve, to actually factor numbers. And it's really easy to use it from Dsage. All you do is say f equals distributed factor. Can everyone see that? So f equals distributed factor, and then the Dsage instance, and then like a number you want to factor. So see, we can try 2 to the 125 minus 1, and you just hit enter. And if you go to the server, you can see that we've started 10 ECM jobs, and they'll be processed by 2 workers currently. But if we think that's too slow, and those jobs all just got killed because we're already done factoring that number. So if you go back and hit F, we've just factored it. So that obviously it wasn't large enough to show what Dsage can do. So let's try 650. So now what I'm going to do is switch over to another computer. So this is another computer in the math department, and I'm going to run some workers there to help with the factorization job. So, because we only have 2 running, and you can see that by going to the server status page. So I'm going to do Dsage worker, and then server equals Sage 8083. It's false. And how many cores does BSD have? 8?
Unfortunately, 4.
4? Okay.
Should have bought it 1 month later.
So we'll just use 2 of them. So that's going to start two more workers from another computer that are connecting to this Dsage server, and they'll be processing those jobs as well. You can see some of them are going to be faster than others. So let's see. And again, you can kind of monitor the jobs being processed here. The cool thing about the algorithm is that it'll automatically produce more jobs. When, for example, I have like 100 workers and they've consumed all the jobs, it'll automatically push more jobs out there. So you can see that it's pushing out more jobs. And if you go back to the Sage console here, you can kind of see the, so it's trying to factor this number, which is apparently what 2 to the 650 minus 1 is. And you can kind of see the prime factors it's found so far, and the composite factors left. So all of the workers right now are probably trying to factor this number right here. And I'm not sure when it'll be done, because it's kind of random, and I'm not really sure how long it's going to take.
It's very hard to tell.
Yeah. But yeah.
So it's one big, how many digits are there?
Oh. And this is my little anti-RSI application.
How many digits are left in the composite factors left?
Let's see.
Can you just do like, yeah.
So it's
91?
91 digits.
It'll finish, but it might be a couple hours.
Yeah.
Or something.
Well, actually, I think I tried something like 2 to the 700 minus 1 last night, and it finished in like 9 minutes.
Depends on mass of it. Basically, the complexity is that of the largest factor.
Yep, exactly.
But
we can try to speed things up by adding some more workers.
That won't help. When you're trying to factor one big number.
Actually, so if we set f use QC equals true, then it'll start some quadratic sieve jobs, and they might be able to. Because you said quadratic sieve is like useful up to.
It'll certainly do it, but all of them will take the same amount of time, and it's not going to help you doing more than one. I mean, there's two algorithms he's using here. One is the elliptic curve factorization method, which is a method that uses these objects called elliptic curves to break off small and medium-sized factors from an integer, so up to like, I don't know, 20 digits or something like that. Then there's another algorithm called the Quadratic Sieve, which at the end of the day ends up doing a lot of linear algebra. And basically, given a number that's a product of 2 primes that are fairly close in size, it factors that. It's harder to parallelize the quadratic sieve if you have to parallelize the individual linear algebra steps and so on. Whereas with the elliptic curve method, if you just sort of trivially run 100 copies of the same thing at once, then your chances of finding those small factors just goes up by a big amount. So for this particular example, I guess it's an Amdahl's law type.
Yeah.
That's going to be the dominant step, so parallelization in this naive way doesn't help so much. But if it's lots of small factors, then parallelization helps a huge amount, because the elliptic curve method will just find them all very quickly.
Yep, and also like the really, really small factors are found by just trial division up to like 100,000. So it'll break off the really small factors first. Yeah, so that's a quick intro to Dsage.
Great. Okay, so shall we swap over? Any questions while we swap? Yeah, Igor.
What it takes so long to compute 2 plus 2 in that first example?
I'm sorry?
Why does it take so long to compute 2 plus 2 in the first example?
Oh, well, because unfortunately there's a lot of overhead when you create these jobs, because you actually have to kind of, so the thing is that the idea is that these workers could be running wherever. So when you create a job, what it has to do is it has to store it on the server, and a worker, say, in some other state could potentially, over the internet, get that job, process it, and send it back. So it's done, so there's a lot of overhead in, for example, serializing that object and transferring over the network and deserializing it. So it definitely doesn't make sense to do it for trivial things like 2 plus 2. But for computations, where the computation time is going to dominate, then it does make sense, because after a while, the overhead is not as important anymore. Does that make sense?
I mean, there's different models of doing parallel computation. One where you have a persistent connection to each of the worker processes, where they're all threads in some single process. And then the other model is something more like GIMP, like the GIMP's project, the Great Internet Center Prime Search. And this is much more like that.
Yeah.
The workers have no persistent connection to the server.
So if you want, if you want to do parallel computation where they actually share memory, you want to use something like P threads, like just native threading. But unfortunately, in Python, you can't actually even use threading, because there's this thing called the global interpreter lock that basically makes sure only one thread is running at a time. So threading is a big problem in Python. You had hand up? I'm sorry? Yeah. So on the back end, the way it stores all its data is just in a SQLite database right now.
Using SQL Alchemy, right?
Yeah.
As a wraparound.
Yep. Okay, thanks.
Thank you. Yep. Right, so now you've seen Dsage, and everything you type, these are just commands that are built into every copy of Sage. So it's not hard if you want to try out Dsage yourself. Now I'm going to talk about crypto for about 20 or 30 minutes. And by the way, here's a picture of somebody, and I misspelled, or I typed out Hellman and Diffie. And these guys are kind of interesting because they introduced the first public key, they publicly introduced the first time a public key crypto system, which was kind of a major shock to the world when it happened. Okay, so I'm going to show you a couple of different tools that are included in Sage for cryptographic applications. And one of them is Pike Crypto. And I'll just give you a quick feeling for about 10 or 15 minutes for what Pike Crypto is and what it does. And then I'll talk about some code that mainly David Hull wrote that goes along with the book. He taught a course several times in Sydney, Australia on cryptography, aimed at an undergraduate level, but kind of an in-depth course. And he wrote a sort of very nice book about what he was doing. So I'll show you the book, show you where to find it, et cetera, and show you some examples of the sort of code that's in the book, some of which is very, very simple, and some of which is more complicated. And then I'll show you, again, an example of implementing a public key crypto system directly in Sage, and just make a few remarks about whether or not you want to do that, and some of the things that are available to you. So I'll start with Pike Crypto. So Pike Crypto is a standard Python library. It's something you can install into any version of Python, assuming you have the dependencies needed to install it, which aren't very much. And what it does is it gives you a reliable and stable basis, including the website, for writing Python programs that require cryptographic functions, like cryptographic hashes, public key encryption, digital signatures, all that sort of thing. this is included in every copy of Sage, by the way, so you don't have to install it into Sage. A lot of the implementation is in C for speed purposes, and it is pretty fast in practice. So let me show you the website right here. So this is a Pike Crypto website, and the point of this mainly is if you're going to build some sort of Python or Sage program that will involve cryptography instead of implementing, say, a public key system or a symmetric system from scratch, which A, will take you a while to do possibly, and B, will possibly have bugs in it, and C, have bugs in it that will cause your system to be easily broken by a nefarious hacker, you can instead use this implementation, which has probably whatever algorithm you were planning to implement, and it won't take you any time to just start using it. And if there are any bugs, instead of them being your fault, they're his fault. So maybe you feel a little better and you get to complain to him. And also, fortunately, this has been used by a number of other projects, so it's more likely that bugs would have been found than some brand new code you just wrote. And hopefully, this person, Andrew Kuchling, is hopefully a little bit more of a professional cryptographer than maybe you are, since he spent a lot of time implementing all this stuff. Clearly cares a great deal about cryptography, gets paid to do it, so maybe he'll have done a better job. So the first point to look here is that there's a list of the different things that come standard in Pike Crypto, which again just comes in every copy of Sage. So a couple of different hash functions, some block ciphers like AES, Blowfish, DES, triple DES, RC5, and so on. There's an RSA implementation, a DSA implementation, LGML implementation, and so on. So there's a couple of different things for doing crypto. Basically all the standard protocols. And they're implemented to actually be used. They're not just toys. It's easy to find a lot of kind of toy crypto implementations out there on the internet, which aren't really meant to be used. Like some student just decided to work through a book and implement several of the algorithms or something. And this is definitely a step above that sort of thing. So to get a sense of what's in the library, there are two things for you to do. If you just have access to Sage and nothing else, and you want to know what's really definitely there, you just type import crypto, notice the capital C, and then you type help crypto. So you import the module and then you say help of the module name. By the way, in Sage right now, sometimes when you do help, it always does word wrap, and the word wrap can make it a little bit difficult to read the help. In order to toggle whether or not output is word wrapped, you just click to the left. I'm going to change it so that help by default doesn't word wrap, but that's not done yet. So this lists each of the different packages that are in Pike Crypto. So there's crypto.cipher, hash, protocol, public key, and various utility things. And in order to use each of these, you import the corresponding module. So if you want to use, say, hash functions, you do import crypto.hash, and then you just type help crypto.hash. And then you'll get a nice little page that describes what's in there. The annoying thing is you can't just say crypto.hash.tab and get nice, useful information. I don't know exactly why, but you can't. But as long as you know to use the help function, things work fine. Here's an example of using the hash function, which I would figure out how to use by doing help, first doing import crypto.hash. Actually, before I do that, note that if I just do crypto.tab, I'm disappointed, because in fact it doesn't even list hash as an option. But if you do crypto.hash, it is there, and you can say crypto.hash, say help of it. You'd like to be able to do just crypto.hash.tab, but you get absolutely nothing. So it's annoying, but fortunately if you do help, you will get help on crypto.hash. And the help's actually pretty good. Has an overview of what's there, and then it tells you each of these other modules that are included. And again, if you import any one of these and type help of it, you'll get nice help. So it's just a little different than the help in a lot of the other things in Sage or Python. So let's try one of these things out. This particular example, computing an Md5 hash of a certain string, which is one of the things that's included in Pike Crypto. Of course, there are other ways to get that kind of information. I found it by looking in the Pike Crypto documentation, which is pretty comprehensive. So this is an outline of the documentation. You can find it on the Pike Crypto website. And it has a number of examples, some of which require a very slight amount of tweaking to get to work, unfortunately, but it didn't take me long to figure out how to get them to work. This one works just as claimed. So I just pasted this in, and that's what I'm going to show you. So there you are. So what's happening here is we import the Md5 hash, make a new instance of it, initialize it that string, and then compute the actual hash. And there it is. And you can also view it as a hex string, which is a little bit prettier. So simple. Yes, E.
I just want to mention that the Md5 module is actually built into Python.
Yeah. If you build Python in the presence of I think it calls a system library, so it may or may not be there depending on what is there when you build Python. But if you've built Sage, you definitely had it there, because you can't build Sage if Python didn't get Md5 built into it. So, yeah. So I mean that's one instance. He's trying to be. So there's import Md5. This is something built into Python nowadays, and I mean you can see if it gives the same answer. So that's nice. Consistent results. This is the one that's built into Python. This is the one that's included in Pike Crypto. They're completely, a priori completely different. I don't know whether this is a new implementation he did of Md5 or if it's calling some system library. I'm pretty sure this one calls a system library, though. Or at least depends on the system library. Just out of curiosity. It's always fun to race cars. Okay. Surprisingly similar timing. Suggesting that, I don't know, maybe they're calling exactly the same code behind the scenes. Yes. We could try a bigger string that might tell us something. Very, very similar timings. Actually, often when trying to figure out, say, what another program does that's faster than your program, you benchmark various bits of it, and when the timings match up identically, then you know you've figured out what they're doing. This is used a lot. It's not very useful. Reverse engineer things. Okay, moving on. So here's something where you can type in, say, your name, and it will give you the Md5 hash. So the fun thing here is you can just see how changing, one letter completely changes the hash. That's all. I already showed you this. There's another example with a different hash function. So this is the SHA hash and the timing adapt. Okay, moving on to the next module. There's a whole bunch of different modules, as I showed you. So here is crypto.cipher. So this has a whole bunch of symmetric ciphers. So by the way, the general kind of pattern for doing cryptography these days over the internet is that using some sort of public key encryption method, maybe Diffie-Hellman or RSA or something else, two people who want to communicate agree on a secret key. And they don't do it by calling each other up on the telephone. They do some sort of magical mathematical operation. For example, the Diffie-Hellman key exchange, which I'll show you at the end, which allows both parties to agree on exactly the same secret, even if somebody else is watching all the transmissions back and forth. Then using the secret that they both agree on, they choose some symmetric cipher, possibly one of these, or in fact very likely one of these, and then they use this symmetric cipher where both people use exactly the same key to encode messages back and forth. And the main thing about these symmetric ciphers is that they're extremely fast, and the hope is that also if you have a lot of known plain text and the corresponding cipher text, you can't figure out what the key was needed in the cipher. And basically these ciphers involve kind of scrambling. There's some key that defines some procedure that scrambles a message over and over and over again via some sequence of operations. And that scrambling is undoable if you have this secret key. And these are meant to be very, very fast. That's kind of the main point. Very fast and difficult to break. So let's try one of these out. Okay, so first I've imported the DES, Data Encryption Standard module from crypto.cipher. Then I made a new instance of it with this as the secret key. By the way, if you look at the tutorial, they just say des.ecb. But if you do tab completion, you'll notice that it's really mode underscore. So that's something that's slightly different in the documentation. Anyways, so I create this object, and now this will allow me to do DES encryption and also decryption very fast, very quickly back and forth. So I encode the string. The Sage math software is a space monster, but a good kind of space monster. Which is a quote of one of the lead Harry developers describing Sage. And it's a 77 character string. And if you encrypt it, it just goes, boom, sorry, the string must be length a multiple of 8. So doing a little arithmetic mod 8, we figure out how many spaces to stick at the end to make our string have length a multiple of 8, and then we encrypt it, and this is what we get. Okay, so this is some like raw data that is encrypted using DES, which could then be sent over the internet or whatever. Now in the other direction, let's take the cipher. You just call, first try that. Take the cipher and then call decrypt, and you get back this sentence. Okay. I think might be fun to mess up the enciphering and see what happens. Let's see. I'm going to change the very first letter to an A. Okay? Now let's see what happens when we try to decrypt. What do you think is going to happen? Any guesses? I actually don't know, but I'm guessing it's going to just, well, there's two possibilities. Either it's going to give some error message because there's some sort of consistency check, or it's going to give us completely random garbage out. So how many people think there's a consistency check? Okay, 4. How many people think random garbage? I actually have no clue. We'll see. Random, wow, a little of both. Actually, there's just random garbage at the beginning. There must be a block size. And I've messed up one of the blocks. But the other blocks I haven't messed up. There's no consistency check, evidently. I think the idea is that if you wanted to have a consistency check, which one would you choose? And I mean, there's a lot of different possible codes. Coding theories about making, encoding a message in such a way that if you slightly garble it, you can tell that you garbled it, and then ungarble it. There's a lot of different ways you can do that. If you slightly inefficiently, I mean, there's just a lot of different possible ways in which to put in a consistency check, a checksum or something. So I'm guessing that the idea is that you would put the checksum at the original, in the original plaintext message, and then once you've decrypted it, you would then check that the checksum matches. In other words, since there's so many different possibilities for putting some extra check in, that would be something that would be done at the level of the plaintext on both sides. It's left up to the person using the protocol rather than built into DES itself. So that's what happens. So the message is put into little blocks, and then one of the blocks is scrambled, completely and totally scrambled. Okay, here's an example where you can just this happened. Oh, I'm supposed to put a key in. The key has to have at least, or exactly, 8 letters. Okay, so a message, that's how it encrypts. Let's just change one letter. Let's change, say, the A to a B. And it looks completely different. So let's see, let's try changing just the first letter. from an A to a B. What do you think is going to happen? All I did was change the first letter from an A to a B. So I'm going to change the whole thing, give an error message, probably not give an error message, or what? Yeah, Igor?
I think it will change the first 8 characters.
Okay, let's see. I think it changed the first 8 characters. Yeah, so it just changed the beginning. It moved a little because the characters got wider when displayed this way. By the way, it's kind of fun. You can, if you get rid of repr here, it actually, the browser tries to render the characters, so you get all these funny symbols. Look kind of like, well, I don't know what they are. Oops. Okay. All right, moving on. So this Pike Crypto module in Sage also has a public key module. So just like in every other case, you do import crypto.public key, where the only way you knew to do crypto.public key was because it was listed in the help for crypto itself. You didn't get that by tab completion, unfortunately. By the way, possibly a good student project would be to fix things so that tab completion does work really nicely with Pike Crypto, which is certainly possible. Probably wouldn't be that hard. And then you could contribute your fix back to the Pike Crypto project. E.
What controls your tab completion?
So let's see. So this is at the module level, but I think you could do this. One way you could do this would be to have maybe you have a lowercase version of all of these things and it just makes some shadow class, but that would be kind of lame. But when you hit the tab key, the object that you're tab completing on gets queried. If it has a dictionary, it asks for the keys of the dictionary, and if that fails, it calls a trait names method and takes the list of strings that you get out from that. So this module crypto, or the submodule public key, etc., these are even a Python module is just a Python object. So it can have a dict method, it can have a trait names method. So you just have to define the appropriate method inside of each of those modules. They're probably coded as C extension modules, so it could be pretty painful. One alternative, though, might be to just possibly make some sort of just pure Python or Python classes which have the same names as these, except they just shadow the original ones, but for which tab completion works perfectly. And then you just, I don't have time to explain that idea too much. This is certainly fixable. It would be much friendlier if this were fixed. Also, there's no examples in here in the documentation, which I think is really unfortunate. Like if you look at des.new, for example, and the tab key, instead of getting nice examples, you get just the kind of calling signature and a quick description. So it would be really, really nice if this had some examples of how to use it. And that it would also be nice if they were automatically tested. For example, the user's manual for Pike Crypto, it's pretty clear if you try it out for a while, you'll see that it's clearly not automatically tested because there are little fiddly things that don't just work when you paste them in. So the quality of this could be improved in a fairly straightforward manner, I think. All right, so let's do an example involving one of these crypto systems. So notice there's quite a few different crypto systems there. So let's try RSA. And the way it works is you import, not sure why Md5, oh, Md5 is going to get used here. So we import the RSA function, or object or whatever. Then there's something called RSA.generate, which creates a new RSA key. It takes the number of bits of the key and a function ranfunc, which takes as input an integer and returns a string of random letters of the length equal to that integer. And I'm doing that, I just implemented my own little ranfunc in a hurry that does that in a pretty darn stupid way, as I call the system random function and take the 4th digit of that random value and then string them all together. It's a pretty stupid way of generating n random integers, or n random letters, but I just did it because I was in a hurry. And you can see using that, you generated a 1024-bit RSA key in that amount of time. what this means is that internally what it did was it chose two primes that are roughly 512 bits and then multiplied them together. And it also chose an exponent, which that won't make much sense if you don't know what RSA is, but anyways, it's an example of a public key crypto system. So here we're going to encode a message by first hashing it. Actually, we're going to sign a message. So we sign the hash of the message by encrypting it. So the way digital signatures work is you take a big message, you compute a hash of the message using a hopefully very, very good hash function, and then you take the hash and encrypt it to yourself using some public key system such as RSA. And actually, you decrypt it to yourself. Kind of funny, so that anyone else. So what happens is the following: first, you have your big message, then you compute a little tiny hash of it, and then you pretend like it's the encoded. You pretend like it's a message that you want to decrypt, so you decrypt it using your public key. And you get this, and that's the signature. And you just append this at the bottom of your message. And the way this works is that anybody else can then take your message, they can compute this hash, and then they take this decrypted version of the hash and they encrypt it to you. And when they encrypt it to you, they'll end up getting this, which proves that you're the only person that can decrypt it. So when they encrypt it to you, they end up getting this thing right here. So they verified that the message was really written by you. The key thing, though, in order for this to work, is that there's no easy way for somebody else to construct another message that says what they want, but it has the same hash. For example, if your message says, it's pertinent that we do not bomb a certain location, right, use a ridiculous military analogy, you don't want some adversary to change the message to it's pertinent that we bomb, if they change, if they delete a few letters or change the letters slightly, they completely change the meaning of the message and destroy the world. So it's very important that it's not easy to forge a message that has the same hash. Or maybe more close to home, maybe the message says deposit $1 million in your bank account, but somebody changes it so it deposits $1 million in their bank account of your money. That would be bad. So that's how digital signatures work. Just one example. So there's some function called RSA key that will verify that the digital signature is correct, and another one that, well, I mean, if you try it and the signature is wrong, then it fails, which is good. Okay, moving on. Any questions about Pike Crypto before I go on? Again, it's the library that's described at this location. Okay, so the next thing I want to show you is David Cole's course, which I think is pretty nice. Here's the webpage for the course that he taught on crypto, and it's really aimed at solidly aimed at undergrad level. He wrote this book right here, which I've just downloaded, and I will pop up. Let's see. Is that it all? Yes, that's clear. So it has a bunch of discussion about classical cryptography, cryptanalysis by analyzing frequencies of letters appearing, etc., block ciphers, stream ciphers. Basically, many of the things I've just been demonstrating to you, but described in a way with lots and lots of examples and code and so on. And then some elementary number theory, and then some discussion of public key crypto, and finally digital signatures. So that's the whole book, what I've been trying to explain to you in 10 minutes. So obviously, if you don't know it already, you probably won't get much in the way of depth. One nice thing, though, is that the examples in this book, if you look, there's tons and tons of Sage examples in here. So you can see there are all these examples of the various crypto systems. And a lot of the kind of background code that gets used here is included standard in Sage. So you don't have to install anything special in order to use it, as you can see. So if you want to learn a bunch about crypto, this is one good place to look. And a nice thing is that David Cole is a serious arithmetic geometer who I went to grad school with, so he kind of knows what he's talking about mathematically. So that's this book, which is of course freely available. And here's just one example from the book. So you create a substitution cipher. This is the message we're going to encrypt. We're going to generate a random key. So this is a really boring cipher. It sort of just randomly permutes the letters. It's not a very good one. So let's see. Somebody encode that word. So first, I take the string and encode it, and then I actually encrypt it. What this does is it just permutes the letters as described by that random choice of a permutation, and then this decrypts them. Whoops, looks like I called it decrypt rather than decryptor. Let me get back to the original thing. So you can encrypt and decrypt. It's very simple, but there's just a ton of stuff like this that goes along with the book that's in Sage. Okay. Finally, Sage itself has really, really good support for a lot of the objects that come up in public key cryptography. So integers modulo n, elliptic curves over finite fields, generation of large primes efficiently. For example, Sage's primality testing, which it inherits from Paris, is actually extremely good. Actually quite a bit better than Magma's primality testing and a lot of other systems. And in practice, like Speedwise. So there's really a lot, if you want to do research on trying out some idea for a public key crypto system, there's a lot of functionality in Sage that's good for this sort of thing. I think Magma is definitely a bit ahead of Sage as far as an environment for trying out ideas for making and breaking crypto systems in the public key context. So it's really, really, really been developed in that direction for the last decade. It's certainly way ahead of every other system out there. But Sage is closely catching up to Magma as far as being a research tool for public key crypto. This is just a really, really simple example, which I have showed you before, where, well, here's the example, which should look familiar to you, where you choose, I'll do the simplest example, you choose a prime, a base, and you do this arithmetic, and you end up agreeing on the same shared secret. And it's fun if you make this a bit bigger, and you get a bigger secret. And the main thing to notice is that these two numbers are the same, but the numbers sent back and forth and kind of showed publicly don't easily give you the information of those other numbers that are the same. By the way, when I first showed you this on the first, I think on the first day of class, it got really slow when I moved the slider to the right. It got ridiculously slow. And the reason for that was that finding a generator for the group of numbers modulo, non-zero numbers modulo p takes a while, as it turned out. So you don't really need a generator for this algorithm. So in the case when the number is big, I just chose 2 now. And then it's a lot quicker to watch it go. But here's the actual code. So finding a random prime, that's something Sage is very good at. Making a finite field, you just say GFP, makes the finite field. Then you choose either a generator for the finite field, or if you just want to be quick, 2, in the case when the finite field is big. Then you choose 2 random elements, then you do the arithmetic that's involved in constructing the crypto system, which after you've done the above is completely straightforward. It's just kind of given in the output right here. But if you wanted to, say, do something similar with elliptic curves over finite fields, it's equally easy. You can say E equals elliptic curve, make the finite field, say GF next prime 10 to the 20, defined by this equation. So an elliptic curve, it's an object very much like it's an additive abelian group, very much like the integers mod n. It's just that if you know a number and a multiple of that number, it's really hard to figure out what the multiple is. That's kind of one of the most amazing things about elliptic curves. So if I knew a specific point on this elliptic curve, which I don't, but if I searched around for a little while, I'm sure I could find one. Actually, 0, looks like p equals e 0, 2 is a point. Right? Yeah, so given p and given q, it turns out that, as far as we know, it's extraordinarily hard to figure out what number you multiply by here. And that's just, seems to be the case for elliptic curves. And because of that, you can construct some really powerful cryptosystems using elliptic curves. And Sage is a reasonable environment for doing that. Okay, so just quickly summarizing the lecture. First, E gave a demonstration of how to do one of the many ways to do parallel computation using Sage. Python has a lot of different parallel computation frameworks, and the thing that E's worked on is just one of many. Second, I showed you the Pike Crypto library. Third, I showed you David Cole's book. If you want to kind of dive more into crypto, that's a nice book that uses Sage. And then fourth, I just pointed out that Sage has a lot of basic infrastructure that's really, really useful for experimenting with public key cryptography. Okay, so now I'm done with the lecture. Any questions? Okay, cool. All right, I'll see you all on Wednesday. Remember to bring in your homework so you can hand it in on Wednesday. And